So I'm going to give a sort of brief overview of a few gems of C++11. There's way too much to cover, so I'm just going to pick out a few things, and I might have picked the wrong things. There might be things that are more sort of valuable to put in here that I missed, but you know, what are you going to do? Maybe next time. Also, a fun factoid. This last Sunday, C++11 turned 2 years old, exactly. It was published September 1st. All right, so let's get started. This is the list of things that I ended up with. Some things that might be obvious, some slightly less obvious. I don't know how many of you know anything about C++11, but this essentially ends up being 4 core language features and 3 new library additions to C++, which is great. So let's get started with for loops. This is kind of a small change, but a very welcome one and a very awesome one. It significantly simplifies writing for loops, especially making the common case of for loops much less error prone, because typically when you loop over things, you loop over the entire thing and you do something with it. So let's start with looking at the C++98 way of doing for loops. First one, you have an iterator. You grab the begin iterator and you compare it to the end iterator, and you increment it each step, and then you do something and you dereference the iterator. This is kind of the generic way of doing it. And if you have a C array, you could take a pointer or you could take an index like this and you iterate over it, and you do the old hack of size of divided by size of 0. There's a lot of stuff going on here, and if you want to be sure that you're actually looping over the entire iterator and that it's actually doing what you would expect, you actually have to carefully inspect all of those lines to figure out, to be certain that that you're looping over the entire container. And you also have to inspect the entire loop body, in fact, to make sure that no one is tinkering with the iterator here or tinkering with the counter there somewhere in the loop, in the body of the loop. So imagine in a real case scenario, you might have a much bigger loop body than a single line. In C++11, you can write it like this. You say int a colon v, assuming that v is a container of ints. And this means loop over v, and for each iteration, a is the next item in the loop body. So you can notice that there's no iterator here. There's no way for the loop body to screw you by moving the iterator back and forth.
That looks only 2 decades over here.
Yes. But they got it right instead of getting it wrong first. Another notable thing is that there's only one version of this. So v can be an STL iterator or a C array, and in fact it can be any container that you write as well, if you make sure that you satisfy the requirement of that type. The for loop can sort of be thought of being expanded to something along these lines. Probably not exactly this, because there might be some other edge cases that you run into that fails. But conceptually, you can think of it like this. You have auto I. We'll get into auto later. It essentially means just whatever begin returns. And then end. Oh, wait a second. End is a function call. And it returns the end iterator. And I obviously have a bug here. If you spot bugs, by the way, feel free to yell them out. I put some bugs in just so that you can see if who's. Yes?
So can I be a jerk now, or should I wait till the end?
No, go ahead.
Okay. So what can the begin, for instance, can begin throw?
Yes.
So like in that previous slide, what would happen if...
You're saying that you might not loop over the entire body if you throw.
I'm not saying anything. But maybe Bjorn Straustrup should say something.
Well, let me fix this right away then. Oh, it's going to be uglier, but who cares? Oh, you still have my schedule there. Okay, so what this means is that we declare I and we declare underscore end. That's the old C way of declaring multiple variables in the same line. So we declare underscore end and we grab the return value of end at the start of the loop. So if either begin or end throws, you probably won't loop over anything. So I think that you're probably still safe that you either get everything, all or nothing, sort of on the looping. So essentially, so I just fixed the bug. We grab begin, we grab end, we loop until as long as I is different from end, and we increment it, and then we grab the value, and this is the actual loop audit that you put in there. So the genius behind the free functions, not member functions, but the free functions begin and end, is that you can then have an overload of those that takes C arrays. Okay, and now I'm going to move on to this thing that also broke because I had a bug that I hadn't fixed on this slide. There's this excellent feature in C++ called argument-dependent lookup that is very well thought through, which says that when you try to find a function, if you have multiple overloads of a function, you first look in the namespace, in the same namespace as the arguments that you're calling. This essentially was primarily introduced for operator overloading. If you write your own type in your own namespace and you want a plus operator on it, you want your plus operator to be the one that's found first, not someone else's plus operator. So it's going to look for plus operators in the same namespace as your type. It can be used for regular free functions as well. And in this case, it means that if v is your own type, you can also write a begin and end function in your own namespace, in the same namespace as that, and it will just work in the for loop. And the standard provides begin and end for C arrays, and obviously for all of its containers as well. In fact, I believe the default begin and end will just expect that whatever you pass in has a begin member function and an end member function. So that's very clever. This is sort of also probably not exactly accurate, but sort of conceptually accurate. You can think of it this way. The standard provides these functions for C arrays. So this is an array of type A's with n elements in it, and it returns the pointer to the first element and returns pointer to one past the end of the C array. That's for loops. Excellent. So next up is automatic type deduction. So remember that auto keyword, which is new? Many of you might have heard about it already. That's sort of what I'm going to cover briefly right now. The automatic type deduction is a way for you, as the programmer, to leverage the automatic type deduction that the compiler already has, but hasn't provided you previously. There are two new keywords. Well, actually, the keywords aren't. The decal type is a new keyword. Auto is an old keyword that has been recycled. Only a few people know what it used to mean. So auto can now be used as a type. It can be used as a type when you declare a variable, and you can only use it when you declare a variable and you assign a value to it at the same time. And it will essentially resolve to the type of the thing that you're assigning it. So you no longer need to know what something returns in order to capture it in a variable, which is very convenient sometimes. And I think there will be an example of that. The other keyword, which is a little bit more obscure and probably less useful, it's more useful when you're writing libraries, especially template libraries, is decal type, which is an expression that resolves to a type, and it can be used in type expressions, which again are primarily used in templates and primarily useful in templates. But it means that you can write decal type and any expression inside the parentheses, and the whole expression will resolve to the return type of that expression. Also, feel free to interrupt me or ask questions or tell me that I have a bug or something if I do.
Is decal type used like a function?
well, it sort of looks like a function. Its closest comparison is really size of, but size of still size of yields an integral constant. So that's still used in regular, like normal expressions. Decal type is used only in type expressions because it yields a type.
But it's just a compile time thing. It's not actually a function in any way, shape, or form.
Exactly. So here's an example of decal type, which all of my examples will be kind of contrived because I unfortunately only spent essentially last night and a few hours before then to throw this together. So what this means is, let's say we have a function f. We want to declare a vector of whatever f returns. So you can say this is a template. So within these brackets you specify types. Decal type will resolve to a type, and the expression in here means, the type of this expression is the type of the decal type expression. So we'll get a vector of whatever f returns, and then we can generate and call f 10 times and push that back to this vector. A little bit contrived example, but the interesting thing here is that no one knows what f returns, but this would still work. One key thing here that I mentioned once is that f is not actually called here. This expression is never evaluated. Similar to size of. When you have size of and you put an expression in there, you don't actually evaluate that expression. You just determine what the size of that type is.
When you're making a collections type class, something that has parameters to it for its type, can you use decal type on methods of your parameters?
Do you mean template parameters?
Yeah.
Or that's what I'm doing here, or is it something else? You can have.
Well, it's not clear from the context here what f is. So f could be like a variable. I guess f is a function, but f could be like a free floating function.
Yes.
But it could also be like a method of one of your parameters or something like that.
I believe it has to be either a free function or a function object, except in this case, I believe this syntax actually requires it to be a free function. If it's a function object, you wouldn't have the ampersand there. You just. Okay,
so it has some limitations on it.
No, I'm just saying that this example, in this example, it's a free function. This expression can be any expression that is valid.
Okay.
And decal type looks at the type of that expression, the resulting type of the expression. So it's more interesting perhaps if you are a template function and you take two template arguments, and you know that one of the requirements for your function is that you can add these two template arguments or these two unknown types together, and you yield some other type, and you don't know what that is, but you can do decal type a plus b, and then you sort of can capture what that is and capture that in a variable. Any other? Awesome. Right, and auto, this is sort of comparing it to C++98. This might be a slightly less jaw-dropping example, but let's say that you have a map of strings to ints, and you want to see if you have something called foobar in there, and if you don't, return. And if you do, you want to use I for something. This is how you'd write it in C++98, because you have to grab the iterator, compare it to end, and then do something with it. When you have auto, you get a little bit more convenience, because you can just say, I don't really care what kind of iterator it is. I just want to grab it and compare it to end. And one other benefit of this is that you can actually change your implementation to say, oh, by the way, I want an unordered map or something else. And all of your other logic, as long as it's still well formed, will just keep on working. Right. I sort of mentioned this briefly. Essentially, what it means is that we're declaring a variable of some type, and the type is deduced from the type of this expression on the other side. So you can sort of conceptually think of it as being implemented in terms of decal type. You take this expression, you pass it into decal type, and that's what you get on the left-hand side.
And in theory, you can do that same
Yes, unless someone here says that you can't. I haven't actually, this is another thing that I might want to admit up front. I haven't actually tested all of these snippets. So anyway, it's an exercise for you guys to spot the bugs that have slid in.
That one's weird because foobar is a specific call. So just to say that that's...
Well, this is an expression. You can have any expression in here.
Oh, I guess I can infer. Right.
You can have things that are valid expressions, but would be invalid at runtime. Like you can pass in, you can say, you can cast a null pointer to a sharp pointer, right? And that would probably crash at runtime, but it's not going to be evaluated at runtime, so it doesn't really matter. All right, that's automatic type detection. Next exciting thing, this is a big thing in C++ 11, is the lambda functions, which also is very exciting. It's kind of understandable that it's taken this long to get it in, because there's actually some edge cases that are not trivial to get right. So essentially, function, I named this function objects. A lambda function or a lambda expression yields a function object, like an anonymous function object that you don't see anywhere, and it can be passed around, and you don't actually know what type it is. Conveniently enough, we have tools to deal with types that we don't know what they are in form of decal type and auto. So it's actually implementation to find exactly what type they have. But the properties that they have is that it's an object that has a function called operator on it, and you can call it, and your code is run. So let's start with C++98 to sort of get a grasp on what's actually going on under the hood. This is what you did previous to C++11, or let's say previous to 2003 at least, to be generous. We want to find the first integer in a vector that is divisible by x. So we use the find if algorithm, and we pass in a function object is divisible by and say x. So this means that x is not a constant. It's something that is determined by runtime. So since we have state associated with this function, it has to be a function object so that it can capture state, namely x. So we create this struct that has a constructor that takes our denominator, it saves it in D, which is a member, and it has the function called operator on it that takes n, and then it returns whether or not n is divisible by D. So people weren't very happy about this, because there's a lot of code for a very simple concept, and also you get the code sort of not where you would expect it to be. It's not down here, it's somewhere over here. So it's very important to name your functions reasonably so that you understand what's going on. And if you want to follow the flow, you actually have to sort of jump around, and it's inconvenient. In C++03, this is not technically a new version of the language, but there was a technical specification that was published as an official ISO document at its time, introducing a few more standard library components. One of them was bind, which makes this actually significantly better, because now is divisible can be a free function that takes two arguments, the numerator and the denominator, and it returns whether or not it's divisible. And then later down here, you use bind to bind one of the arguments to a value and not bind the other arguments. So the result of this expression is another function object that takes one argument and always passes in x as the second argument.
Still ugly.
Sorry?
Still ugly.
Yes. So this is also known as partially applied functions in the functional programming world, where you, as I just described, you have a function that takes two arguments, you bind a value to one of the arguments, and it yields another function that takes a single argument with the one argument pre-applied. So what you do in C++, what you can do in C++11 is that you can write all of this code in line with the lambda function or lambda expression, which makes it a little bit easier to read. For instance, you can notice here that you just say x here, even though it's inside this scope. So x is actually automatically pulled out of the context around the expression. You take one argument, int n, and
open square bracket equals close square bracket is universal for lambda.
I'll get into that a little bit, but it means that you want to copy x into this function object instead of taking it by reference. Now when I look at it, there might be a missing return here. I think you might have to say return here. Do you know? Although, so even though you say return here, the return type of this function is also implied by the expression. So you save a little bit of time or typing of not having to say that it's a bool return value. So here are the key sort of aspects of lambda functions. There's a new syntax, which is the square brackets, the parentheses for taking arguments, and then the body for the function body. The lambda expression will create an implicit function object, which is the thing that I showed on the first slide. It's actually creating that behind the scene. So it's not creating a free function like a C function, because C functions can't capture state. Values or variables that are referenced inside the lambda expression body are captured from the sort of enclosing context. So to go in a little bit more details of this example, this is a capture expression. Equality sign means copy. So x here, for instance, then is copied from there. So I added a little bit of context here. It's actually copied into this function, the function object that is resulting. N here obviously refers to this n. And the capture expression is kind of an interesting part, because by default, most of the time, you probably want to capture things by value or by copy. But sometimes you don't, because that's how C++ rolls. Sometimes you want to do things more complicated. So you can actually say a bunch of different things within the square brackets. In the example, I had an equality sign, which means capture all variables that you mention by value or by copying them. If you say an ampersand in there, it means capture all variables by reference, which means L values. That's kind of language lawyer speak for something that you can modify. So if you have a value outside of the lambda expression that you want to be able to modify inside your expression, you do that. If you want to mix so that some variables are captured by reference and some by value, you can actually specify them exactly by ampersand value and equality sign and or variable. So you can specify individually for each value that you want, or each variable that you want to capture, how to capture it. Yes.
I'm wondering if you can specify that it's const.
I'm not sure actually. I'm not sure if you can do that.
Probably inherits the const.
Well, if it is const in the surrounding context, then clearly it would be const. Yeah, I'm not sure actually if you can do that, if you can force it.
Also, another thing is if you define like x, and when you define a lambda, you change x later on, it's going to be reflected when you call it lambda, right?
Only if you capture it by reference. If you capture it by copy or by value, it's going to be copied into the function object at the time of instantiation. Similar to how this example, in this example, here you instantiate an instance of is divisible by x, and x is copied into D. So this instance has captured X. If you would somehow capture this instance, save it on the stack, and then change X, from the is divisible by point of view, X would still be whatever you passed in. That's capturing by value. If you put an ampersand there and an ampersand there, you would capture it by reference instead. And that way, if you change X later, this function will see the updated value. Does that answer the question?
Yeah, okay. So I guess I was thinking that either the pass by reference or the pass by value happens when you call your lambda, not when you define the lambda.
So the passing by reference or passing by value is defined by your argument list. This is only about the capturing of variables that are not passed into the function explicitly, but things that are captured implicitly. You can capture your arguments just like you capture arguments for regular functions. Like you can put an ampersand here or a const ampersand.
I think maybe what Rob's saying is that perhaps if you had a container that could contain a lambda type, like you use decal type to capture the type of the lambda and stored it away, and then used it at some later point in the function, would you receive the variables copied by value at the time that the lambda value was captured or at the time the expression was evaluated?
I can only understand how it works by assuming that it's when you instantiate it. Because if you don't instantiate it, you can return it, and the values that you captured might not exist anymore. Which obviously you can capture those by reference, and then you get screwed when you actually end up calling it. But I'm fairly certain that you capture by value. That means when you instantiate the function object, that's when they're captured.
This is by value, not a deep copy, right? So if you pass like the vector and then modify the vector, it'll be modified.
No.
By value means that you consider the entity that you're capturing as an object that you copy, which means deep copy.
Oh, really?
Unless the things inside this vector are reference counted. And
it's also up to your object how it behaves when you use the syntax that should mean deep copy, so you can get boned that way too.
Yeah, deep copies inherently.
well, if you're having problems with deep copies, you probably don't want your items to have copy semantics. You probably want them to have reference semantics, like you want them to be pointers.
Well, it gets expensive doing all the deep copies.
Right. Right. Clearly, you should only do it if you need it. What else? I think I covered everything on this slide. So, at least on this slide, I remember the return statement. Sometimes it can be a little bit confusing to the compiler to understand what return type you want from your lambda function. Consider this example where, let's say we have a vector of doubles and we want to clamp small values down to 0. So we use the transform and with this if n is less than 0.1, return 0, else return n. At this point, it's actually a bit ambiguous because 0 is typically by default an integer and n clearly is a double. So the compiler will be like, well, are you trying to return an integer or a double? So you can say, you can use this arrow syntax and say double after your argument list to specify that this is in fact double is the return value of this lambda function.
Wait, why?
There's
I don't understand.
there's actually this syntax with the arrow and return type is actually, it extends to normal functions as well these days. It turned out that when you want to get fancy, let's say you want a template function that does template A plus template B and returns the result. Your return type depends on both of your arguments, and it would become very hairy if you would be able to refer to your arguments before you declare them in your function body. So that's why you are also allowed to specify return types at the end of your argument list.
It becomes totally unnecessary.
No, well, you have the same problem. If your return type depends on n, you need to be able to refer to n, and if you would put it here, n wouldn't be in scope yet. So
okay.
Anyway.
But you can't say like auto n on your declaration that would be a serious no-no.
Right. You might be able to in a year from now.
Oh.
In C++ 14, they're going to probably relax the lambda so you can have sort of implicit template lambdas, which is pretty exciting.
Okay.
Getting pretty close to Python. All right. That was lambda functions. This is an easy one, and maybe a lot of you have run into this problem. Override specifiers. So obviously, whenever you start a new C++ project, the first thing you do is to define your shape class and your rectangle and your circle, right, to derive from it. So something along these lines. And can someone spot the problem here? Yes. Oh, they're structs actually, so you don't have to say public. So the problem is that your rectangles won't ever get drawn because the rectangle's draw function is const and the one in the base class isn't. So it'll just create another virtual function, but not the same one as the one in the base class. So the way you solve that in C++ 11 is that you say, all right, that's a description. It's not actually overriding. So the constness at the end there is part of the signature. So the const function is a different signature than the non-const function, and hence they are different and not overriding. Sorry?
Isn't it convention to put the const first?
Then it affects
on a member function, you put it at the end. And it means that the member function doesn't mutate the object that it operates on.
Oh, okay.
Right. So what you can do is you can say override. So when you write your draw function and you intend to override something from your base class, it's a good habit to say override afterwards, because in this case the compiler would say this is wrong because this is a different signature. Obviously it would extend. Obviously it would extend beyond just const issues. If your draw function took a color, for instance, that would also be a different signature.
It arguably should be required to do that anyway.
Well, sometimes you might want to introduce new virtual functions.
Right. No, but if you are overriding something, you should have to say override.
Yes.
Otherwise, you don't know whether it's overriding.
C#
Right.
does that.
Yeah.
You can do it in C#.
So what's the obvious counterpart to this new keyword? Let's take another example. Let's say that shape derives from entity, and entity has a virtual member function called move, and you want to make sure that all of the shapes use this move and never override shape.
Yeah.
The rectangle might violate that by saying, I'm going to define my own move anyway. However, you as the implementer of shape can then say final. If you say final at the end of a virtual function declaration, it means that you don't allow any subclass to override it, and this would yield an error, a completion error. Very convenient. Primarily override is clearly convenient. I assume almost everyone who's done some significant C++ has run into that, been bitten by that problem.
Yeah. And also, if you say override and it's not there in the superclass, it'll tell you if you typoed your method name, right?
Right.
Yes. That can be very bad.
Right.
Why would you make it a virtual function method if you're going to make it final?
Oh yeah. So to solve that problem, I introduced entity here. Let's pretend that there is another entity-based class that has it as a virtual function.
Right.
So there might be other entities that. Yeah. Right.
So if it's a base class, does it tell you like what are you trying to do because it doesn't know what you're, or does it just treat it as final?
I'm not sure what the question is.
Let's say you didn't have entity and shape is your base class. If you do
Right.
that, it obviously doesn't make any sense. But does the compiler tell you anything?
I'm not sure actually. Maybe it will make it non-virtual and optimize a little bit for you. Who knows? But you're right. It doesn't make any sense. Cool. That was an easy one. So now we're moving into C++ standard library territory, there's some pretty exciting, like I'm skipping the obvious ones like regular expression parsers and what else? Function binders, we touched a little bit. All of those exciting things, hash maps, hash tables, sets, and
I have a question about something you were going over when you're talking about for loops. Is there still no multi-assignment? Can you still not say A, B equals B, A, A, B equals B, A?
Oh, you mean to swap?
Yeah, or anything like
you
that.
You can call std swap.
Because there was one of the examples when you were doing for when you said auto I, it seemed like you should be able to say auto I, comma something else.
There's a standard tuple type now.
Oh, there is. Okay.
Yes.
But there's no tuple syntax. You have to write that whole line.
I might not be Python aware enough to understand what you're saying.
Okay.
But
implicitly, Python would make a tuple and assign slots of it.
so this is when you iterate over like a dictionary?
No, it's just a syntactic convenience if you want to like.
Oh, I see.
A bunch of variables.
You declare sort of a range of like this is a list of stuff that I want to iterate over,
Yeah,
and
you can have like a function that returns 3 things, and you just say like A, comma B, comma C equals my function, and then.
right. Yeah, you could return that as a tuple, and then there's probably not a begin and end for tuple types, but you could write one, and then it would just work.
Right, but it's nowhere near as pretty as if you can actually declare them as variables on the same line where there's an assigned.
Oh, I see. You're talking about splitting. You return 3 things and you split it up at the assignment. Right. Yeah, actually, there's a function called tie. So if you declare the variables first, you can then say tie ABC equals something that returns a 3 tuple, and that will split it up. But you can't declare it on the same line. All right. So one of the main library additions, though, I would argue, is the smart pointers. Maybe because it's one of the more fundamental ones. These are not very controversial. They've been in use, for over 10 years now, outside of the standard. But it's kind of fundamental because it means that you eliminate the very large range of types of memory leaks that you otherwise might have. And it just doesn't make any sense not to use these smart pointers, especially now when they're part of the standard. There are primarily there are 2 kinds of smart pointers in the standard now. The first one, that's sort of the simpler one, is called unique pointer. It holds an object that's allocated on the heap, and when it goes out of scope, it will delete the object. It replaces the previous auto pointer because auto pointer has broken semantics and should never be used, really. Unique pointer is very useful if you, for some reason, have to allocate something on the heap, but you only want it within your scope. You can hold it with a unique pointer, and you never have to worry about an exception being thrown, multiple exit points or return points from the function, or being introduced later. It just automatically will delete the object when it goes out of scope. But perhaps the more reasonable and useful case is when you have a function that has to return a heap allocated object. Let's say that you're using polymorphism. So you return a pointer to a concrete, the pointer is to a base class, but obviously you return a pointer to some concrete object that's unknown to the caller. Previously you would have to return a pointer, and you would just sort of by convention say, the caller of this function is responsible for deleting the object. Now you can return a unique pointer so that the caller of the function receives a unique pointer, and the object will automatically be freed unless the caller specifically asks it not to be. So you sort of you flip it around. You have to put effort in to get a memory leak versus the other way around. So this is perhaps a kind of a contrived example. It's let's say we for some reason A needs to live on the heap and it cannot live on the stack. So we allocate it with new, and we grab it in a unique pointer. We can call functions on it, and at the end of the scope, it will be deleted for us. typically you would want to just create A on the stack in this case. Maybe.
Is A a node?
Sorry?
Is A a node?
A is a class.
Oh.
Or a, yeah.
Yeah, it's a node, right?
Sorry?
It's a node because you have a node in your parameter.
He's saying.
It's fine though, right?
Well, oh right, A could be derived from node.
Yeah.
Yeah, that's great.
A template type that was defined earlier up in the.
Anyway, that wasn't really my intention with this slide, but anyway, good point. +1. Right, maybe the more useful example would be, no typos here. A function that's called getNewShape, and we roll a die and sometimes return a rectangle and sometimes a circle, and obviously they both derive from shape. So, and we want the caller of the function to be responsible for deleting our shape. So this will, without any ambiguity, tell the caller that you are responsible for it, and in fact the caller doesn't have to do anything about it either. That's a good use for unique pointer. However, sometimes you need to have a little bit more. Oh, actually, by the way, there's one interesting thing here. Unique pointer. Unique means that there's always only a single instance of unique pointer that actually holds a pointer to the object, which means that it's not copyable. You cannot copy a unique pointer, because if you would copy it, you would have two instances of the unique pointer pointing to the same object. So if you try to copy it, you will get a compiler error. However, you can return a unique pointer, which didn't used to be possible for non-copyable objects, because you would copy the return value out of your function. This sort of touches on another fundamental new feature in C++11. I didn't include it because it's kind of obscure, and typically as a regular application writer, you don't need to know about it. It's primarily useful for library writers. But essentially what it amounts to is there's a new concept. You can be copyable, but you can also be movable, which means that unique pointer is movable, and you can move this one single instance around. It means you can stick it inside a container. You can return it from functions. You can pass it to functions, but you can only move it into functions. So once you move it in a function, your copy of it will be cleared to not point to it anymore. Very clever. Anyway, sometimes you need a little bit more flexibility. Sometimes you want shared ownership over objects, but probably not as often as you think. There's a shared pointer and an accompanying weak pointer. So this is essentially, yes.
Is unique pointer like something where there's actual code that implements it, or is it a language level construct?
There's code that implements it, but it's very simple.
Okay. Oh, so it just finds out when it goes out of scope because it's on the stack.
Right.
Oh, okay.
Really the only complicated part of it is that you can move it, and you can so you can clear it. So when it goes out of scope, you don't necessarily delete anything, because you might have been nulled by that time. So the shared pointer and weak pointer are, as the name suggests, the shared pointer means that every instance of a shared pointer will keep the object alive. Weak pointer is a pointer to an object held by a shared pointer, but it doesn't keep it alive. So if there's only weak pointers pointing to an object, it will have been destructed. And the weak pointer, you can't actually access the object directly through a weak pointer. You first have to upgrade it into a shared pointer, and by then you will know whether or not the object is still alive or not. Kind of convenient. I'm not actually going to go into the details of the weak pointer, but the shared pointer is just a reference counting pointer, as you would expect it to be. Well, I guess you would expect it to be. And this is one of the most brilliant parts. There's a make shared, which will construct an instance of type A, or T in this case, for you, and return a shared pointer pointing to it. It will construct it on the heap. Which means that you never ever have to call new or delete anymore. with the exception of the unique pointer. That was an oversight, and it will be fixed in C++14. There will be a make unique as well. Once you have make unique, you will never ever have to call new and delete anymore. And in fact, it's probably a good idea to never do that again, because then you will not have those silly memory leaks that you otherwise might have. Another benefit of make shared, it adds exception safety. If you're constructing multiple objects on the heap in the same expression, and one of them fails and throws an exception, if you don't use make shared, if you use raw new and delete, you might have cases where you actually end up leaking objects. When you use make shared, everything is safe. Another benefit you get is that the reference counting implementation becomes much more efficient, because it will actually allocate the reference counter and the object in the same memory region. Otherwise, it will not do that.
But this isn't full garbage collection. It's not checking for cycles or anything.
Right. It's a reference counting smart pointer. So the idea is still that if you have cycles, it's your fault, and you shouldn't do that. You might want to use weak pointer. That's sort of the. Okay, so another.
So weak pointer doesn't increase the count, and it might become null. As you're
Right.
doing.
Right. So the thing with weak pointer is that you can't access the object directly through it. You can upgrade it or promote it into a shared pointer, but when you promote it into a shared pointer, it might be a null pointer. So you have to like promote it, check if it's still alive, and then you can use it if it's there. So here's another slightly contrived example. Let's say we have a socket, we create it, we connect it somehow, and we launch an asynchronous read operation. And we do that with a lambda, and inside this lambda we use C to launch the next operation. The fact that we are constructing this lambda and passing it in as a function object will grab a copy of C, which is a shared pointer. So it will copy the shared pointer, and as long as this asynchronous operation is outstanding, it will actually keep the socket object, or the socket object alive. So after this, we might change our mind and say, oh, okay, let's forget about C. But when this asynchronous function call comes back, it will still be alive, and we will not crash. So that's a kind of a typical case of where you would want to use shared pointers, where you might have multiple outstanding asynchronous operations, all of which should keep the object alive. Yes.
So if you tried to use like a unique pointer in this case, it wouldn't compile?
Yes, that's correct. Because it would try to invoke the copy operator or copy constructor, which doesn't exist.
So you can pass a unique pointer, right, to something else?
If you pass it in as a function, you have to be explicit about the fact that you are giving up ownership. There's a standard library function called move. You can say std move and pass in this object. But so that's a way of explicitly saying I'm okay with losing whatever this thing points to.
All right, but the semantics of I'm passing you a unique pointer, and you must also have it as a unique pointer, and it still must be unique at the time you leave is not supported.
Because then it wouldn't be unique anymore.
Well, no, it's just staying on the stack. I mean, I'm passing it to you, and you're saying it's a unique pointer, so you're not allowed to copy it, but you still only have the one copy, and then when you return to me, there's still just...
Oh, right. You want to pass it by reference then?
Yeah.
Right. Otherwise you would copy it on the stack, so you would have two instances on the stack. Yeah.
Passing by reference.
Yeah, totally.
Huh?
Yeah, totally. And in fact, in that case, if you're just passing it down to a function that will only use, that won't save this pointer and use it later, you could also just pass a raw pointer. But
so even passing it by reference, though, you can't really do the opposite, like break it and pass it down.
You can pass it over.
You can.
Sure.
Right.
yeah.
Yeah, this, you change the equals to ampersand and made a unique pointer that would work.
Right. So in this case, so this is not unique pointer. This is a shared pointer. If you change this to reference, this would not take a copy of the shared pointer, and it would not keep the object alive. And by the time you come back here, the C that this points to might be gone, and you will crash. That's why copy by value is the default, because that's the sort of sane and easy to understand and reason about semantics. All right, that's pointers. Oh, wow, we're running late. So next thing, error code. So is that the alarm clock? So there are a few different ways you can deal with error codes, and historically, obviously the most popular one is to pass integers around to say this is the error. You can also sometimes maybe see that someone passes around a string and say here's the string describing the error. Both of those ways of doing things have problems. POSIX is an example, right, where errno is a very popular way of passing around errors or error codes. The benefits of integers is that it's very easy to programmatically handle those errors. You can always say, is this error equal this constant? And if it is, then I can do something special. If it's some other error, then do something else. It's easy to localize error messages, and in fact, stir error will do that for you probably. What's not so easy is that you don't necessarily know what domain this error code belongs to. Is it a POSIX error, or is it an SSL error? Is it a Windows error? Is it an HTTP error? Is it like a 302 error code or something? It's not obvious all the time. And it's not necessarily very easy to easily interpret by a human either. When you're debugging, you see this error, and you might have to try to call stir error in GDB, and things might blow up, and it's not all that fun. But stir error will probably work, assuming that it's an errno, like POSIX error code. If you use a string, it's easily interpreted by humans. In the debugger, you will see what's going on, probably, if you did it right. It's very hard to programmatically handle the errors. You would have to sort of do string comparisons, and it wouldn't be very robust. If someone has a typo in the string somewhere and fixes it, your program will fail. You still sort of have the problem of what domain the error belongs to. It might be slightly less of a problem if your error strings are verbose enough. But it's essentially impossible to localize unless you have a generic translator, like you pass it to Google Translate and you get it back translated string. So C++11 introduces this simple but, in my mind, brilliant type called error code. It represents an error, and it attempts to solve, and I think it essentially solves all these problems. It has an integer error value indicating the error, which error it is, but it also has the category, which indicates what domain this value belongs to. The category is an abstract base class which does the error value to human readable message translation. And I would like to highlight that this is critical for composability. When you build layers of abstractions on top of each other, errors can happen at any layer, and they can belong to any domain. I sort of have an example later about network programming. Let's say that you're trying to connect to a host. You can either have a POSIX error because something happened at the TCP layer, but what if it's an SSL connection? You could also have an SSL error happen, and you don't necessarily know which one will happen up front. So the error code that comes back cannot just be an integer. You cannot assume that it's going to be an errno error code. It could be an SSL error code, and I don't know if you've seen SSL error codes there. You can kind of tell because they're ridiculous. They're like 32 bits hashes, essentially. But anyway, it could be anything else. Like if you have an HTTP library as well, there could be an HTTP error code. Like you can get 404 back as an error number. So here's an example. This is how you would use error codes in the error code type in C++11. Create a socket, you connect it, and you typically pass in a reference to the error code. And if you got an error, you can check it here. Typically, all functions like this also have a version without passing in an error code, and they will throw an exception with the error code in it. Same thing, just depending on habit or whether you expect the error to happen or not. And you can print out the category name, the value, and the message. Everything a programmer needs. If your user reports an error saying, here's the error I get, and it's in Portuguese. Maybe you don't understand what it is. But if you have the category and value, you can look it up and you can turn it into something that you know what it is. And you can probably Google for it as well, which helps. That's sort of how you use it. And I would say that there's a sort of +1 on each of these. It's easily interpreted by humans because it comes with the category object that will translate it to human readable errors. Easy to handle programmatically because you still have the error code that you can check for and test against. It's very clear which domain the error belongs to because you can ask for the domain or the category. You can even ask for the name of the category. And it's also possible to localize, although it's kind of complicated because you still need to actually do the work of localizing. But at least it's possible. You just need to know all the error codes that you can get.
So,
all right. Yes.
Conditional for error code, what is it used to evaluate to bool?
If the error value is non-zero.
Okay, so it assumes 0.
I think so, at least. There might be a way to ask the category actually whether it should be considered a success or failure. Typically, it means 0 though. Typically, 0 means no error.
Are error codes integrated into exceptions in some way, or is it big?
There is an exception called system error, which includes an error code.
Okay.
So typically, libraries that deal with system stuff like file system and networking and possibly other things, when they fail, they will throw a system error with the error code in it. Or if you pass in an error code, it will be returned through that.
Okay, but is it considered stylistically weird to raise a system error from like a user level library, or is that?
Not necessarily. Like whatever you're doing in your user level library, you might be accessing disk or accessing network, right? So anything, it can fail at any level.
Okay. But then you can have like your own category of exceptions indicated.
Exactly. If you implement your own library, I would imagine that you might implement your own or create your own category as well for errors that happen in your, like in, let's say, a BitTorrent application. You might have BitTorrent errors, things that happen at the BitTorrent level or layer.
So raising a system error with an error code is the active part is considered kind of pressure.
Right. Okay. Right. I actually forgot to mention that, but it is very extendable because you can introduce your own categories of errors, which is something that you can't really do otherwise with just regular integers. All right, let's rush through. We're a little bit over time. Chrono is another one of my favorite parts of the C++11 standard library. It's a timer library, and it's surprisingly hard to do time, apparently. Here are a few questions that one might ask oneself when thinking about the time. If you want to have nanosecond resolution and be able to express time spanning millennia, you can't do that in 64 bits. So there's no obvious sort of, this is the right way of doing time. We use nanoseconds in a 64-bit value because that works all the time. It doesn't necessarily work all the time. And you might not want to use 64 bits. Do you want separate functions for different kinds of resolution of clocks? Do you want floating point timestamps? I know Python people might like floating points. The problem with that is it's kind of odd that you get lower and lower precision the farther into the future you get. Maybe one of the main ones is type safety of timestamps. An example I put there is if you pass in microseconds to a sleep function that takes milliseconds, you're going to have 3 orders of magnitude longer delay, and you might sit there and wait for a very long time. In C++98 and POSIX, we have still the clock and a constant called clocks per sec, which is a terrible function because it's very, very low resolution. I can't recall off the top of my head, but I think clocks per sec is typically less than 100. I don't know if I'm wrong there. I think I've seen it be less than 100 at least. You have the time function, which is second resolution. Actually, you have clock get time and get time of day, and I have a little annotation here. You have very low resolution on the standard clock. You have second resolution on the time. It reports wall clock time or real time, so it's not monotonic. It will get set back and forth whenever NTP D feels like it, or whenever you have daylight savings. You have a clock get time and clock get rest, which is the closest thing to a proper timer that I've seen, at least. It's part of POSIX, but it's modern enough so that some POSIX systems don't implement it, say Mac OS, for instance, and obviously not Windows. You have a get time of day, which is very high resolution, but also not monotonic, because it is real time. Git tick count is a Windows thing, and that's millisecond resolution, which might not be. Actually, it's
Well, 15 millisecond.
yeah, 10 to 15 millisecond resolution. Right, there's a performance counter. There are ways of getting high resolution. There's no standard way of getting good clocks. Right. Monotonic, by the way, is a very important property. When you're writing programs, it's very common to want to say, I am starting this now, take a timestamp, and now do something, and then I take another timestamp, and I want to compare them, and sort of, I want the difference between these two to represent how long it took. If your clock is not monotonic, that will not be the case, and everything is broken. It might work for the most part, but twice a year, it might break horribly. Or whenever you have leap seconds, it might break horribly. So you'll be shipping software that, with this time bomb in it. Terrible, terrible. Monotonic is important. So what kernel does is that it introduces the concept of a clock. Each clock has its own epoch, which is just a fixed point in time. It might be noon, January 1st, 1970. It might be the time you booted your computer or the time you launched your process, whatever. It's not defined. It's just there's one epoch, and it has its own resolution. And the resolution is, this is one tick, and this is how many seconds or whatever nanoseconds each tick is. It introduces two types called time point, which is a type representing a point in time. Typically, it ends up being relative to the epoch. And time duration, which is the difference between two time points, or also just a certain number of ticks. What you do to query the current time is that you call now on a clock, and you get a timestamp or a time point back. The standard introduces 3 standard clocks. System clock, which is the real-time clock like time. There's a steady clock, which is guaranteed to be monotonic, which I would imagine will be very, or is very popular, / will be very popular. And high resolution clock, which is the highest resolution you can find on this system. Note that there's no specification of exactly how high resolution is on these. They're just sort of, that's an implementation detail.
How widely consistently supported are these?
I would imagine that anything that claims to be C++11 conformant supports it.
Oh.
But I would also imagine it to require runtime library support, so probably only newer systems. I believe on Mac, for instance, 10.7 might be the oldest system you can run C++11 on, with all of the library support. So this is the beautiful part. Pretend that there's a type def in front of these. I just couldn't fit it on the slide. Time point and time duration have the resolution encoded in their type, which is brilliant, because it means that so these are type defs for nanoseconds, microseconds, milliseconds, and so on. Assuming that we have a where second is sort of the unit time. So you can see, you can specify the type, the underlying integral type that you want these ticks to be represented in, and then a ratio, which is a template that takes a numerator and a denominator, and the type then. So you have, these are type defs for shorthand. So ratio 1:1 is a second, and 60 seconds is a minute, 3600 is an hour, and 1000 is milliseconds, and so on. You get the idea. The nice property of having the type encoded in, or the unit encoded in the type, is that you can do things like this. You can have a sleep function that takes some milliseconds, and you say, I want to sleep for 10 seconds. And it will automatically do the conversion for you and say, okay, 10 seconds, that's times 1000, because the ratio specified. There's some template machinery behind the scenes here that can convert any time duration into any other time duration, doing the right thing, preserving as much accuracy as possible. To illustrate this, let's say you have a time duration of that represent third seconds and one that represent fifth seconds. So you have 1/3 second and 1/5 second here, and you say, I want to add these two time durations together.
So, so seconds is the, here's my time, seconds is the origin of.
I believe, I'm not entirely sure actually if that's defined or not, but I believe so. I believe the ratio of 1:1 is meant to be seconds.
Is it no longer possible to just like pass an integer into sleep? Will it get mad at you?
That's correct.
Oh, that's good.
I'm pretty sure that's the case, at least. Pretty sure. It would sort of defeat the purpose of if the time durations could be implicitly converted from an integer, because you would lose the property of type safety. This is kind of pretty exciting, I think. If you add D1 and D2 and put it into D, the template machinery in this plus operator will actually make the type of D be this duration int ratio 115 and value 8. It will do greatest common denominator at compile time and figure out that it has to be expressed in 1/15 of seconds and say that it's 8.
Preprocessor does greatest common denominator.
The template engine. And similarly, the comparison operators do work in a similar way, where you can actually compare, if you compare D2 to D1, D2, since it's fifths, 1/5 and 1/3, it will be less.
There's another
Great.
thing in this slide too, which is the right angle brackets. They're next to each other.
Right, this is another excellent part of the C++11 standard. You can have no space in between those. Very fancy. Any other questions? That's actually all I have. Here's a little recap, so you can sort of burn this into your retina, so you remember the keywords, well, the ones that I covered at least. There are tons of more interesting stuff. Yes?
On the lambda, if I did put anything in the brackets, would that be equals in the square brackets? Would
Sorry.
it be equals by default?
You mean if you don't do anything?
Yeah.
Yes, I believe so.
Override and final are only for methods?
Actually, you can say final on a class as well. And if you say final on a class, it means you're not allowed to derive from it.
Oh, trying to copy Java.
Just picking the good ideas. All right, that's all I got. Thank you.